In this video, we'll discuss finding the area underneath a curve. Over to the right, we have graph f of x equals the square root of x, and we're going to consider that on the closed interval 0 to 4. Our task is to find the area between this graph and the x-axis on this interval. So the area that we're looking at is the area of this region right here. Now, when we were learning to find the value of a definite integral and we were building that concept, we talked about the idea of area and the area under the curve specifically as being the area of several rectangles drawn underneath the curve. So if I come out here some distance, and we'll call this just an arbitrary distance out here at x sub I, just some x value in particular, and we look at this rectangle right here, the area of that rectangle is not hard to visualize. We know that this point right here is out x sub I, and it's up, it's a point on the curve, so its height is f of x sub I, or the square root of x sub I. And this point here is, of course, x sub I 0. So the height that we're looking at between here and here, this height, is just f of x sub I. Now, we also know the width of the rectangle. When we were building our idea of the definite interval, we said let's divide the region from a to b, or in this case 0 to 4, into n pieces. Each one of them is going to be b minus a over n, and we call that width delta x. So the area of the ith rectangle, what we're calculating right here, we'll call that a sub I, is the height of this rectangle, which we just labeled as f of x sub I, and the width of the rectangle, delta x, and there's our area. Now, we then said if we wanted to find the total area underneath the curve, then that area is approximated by the sum of all the rectangles that we might draw in here. This is just one of infinitely many, so we said it was the sum of f of x sub I times delta x. And then we later on said, oh, well, if we take the limit of this Riemann sum, as I goes from 1 to n, or from 0 to n minus 1, left sum, right sum, if we take the limit of this Riemann sum, then this thing turns into the area, which is the definite interval of f of x, which in this case is square root of x times dx, and we're considering this on the interval from 0 to 4. And this definite interval right here will calculate the total area underneath this curve. Now, we could do antiderivatives, and we could use the fundamental theorem if we'd like. It's not difficult. This is x to the 1/2, so the antiderivative of this is 2/3 x to the 3/2, evaluated at 0 and 4. So we have 2/3 of 4 to the 3/2 minus 0 to the 3/2. And let's see, this would be the square root of 4, that's 2, cubed is 8, and 8 times 2/3 is 16/3. Now, the really cool thing about this chapter, though, in this chapter, we're going to be far less concerned about actually finding the antiderivative and using the fundamental theorem, and far more concerned with just finding the answer. So we'll be using the calculator to evaluate this definite interval. So rather than doing this, which is perfectly all fine and good, but on the AP exam, if you're allowed to use a calculator, by all means evaluate this definite interval with a calculator, and that answer winds up being 16/3 straight away. Now, recall the calculator command that you need. It's math 9, function integrate. The syntax for the command is the function, so in this case the square root of x. With respect to the independent variable x, you have to put that in there. That's the one that people often leave out. And then the lower bound of integration was 0. The upper bound is 4. Now, on the AP exam, you never write calculator syntax on the exam. But I just put this here just to remind you of how we're going to get this answer. So once you've identified the ith rectangle, and you've said, well, the area of one of those is this, here's the area of all of them, and oh, by the way, that's a definite interval. Once you've written a proper definite interval, then use your calculator to find the value of that interval.